going to need to do is take the what? Magnitude of the vector what? R, which is just your position vector. Your position vector is the vector going from the origin to here. That's x, y, z. This red is just horrible. Let's see if this one's any better. Nope. Well, x, y, z. That's x, y, z. The magnitude of it is its length, right? So you take its length and multiply this vector by its own length. Not divide it by its own length. Multiply it by its own length. Understand? That's what the vector field is, okay? That's the way they're defining it. But for us, what is that? I mean, can we calculate what f is? What's the magnitude of r? Square root of x squared plus y squared plus z squared, right? Times r, which is x, y, z. So this is a scalar, this is a number, and this is a vector. So when we scale a vector, we just pass it through to each one. So this is really just the vector x root x squared plus y squared plus z squared, comma, y square root of x squared plus y squared plus z squared, comma, z square root of x squared plus y squared plus z squared. Close it off. Okay, that's our vector field. Got it? And then I've got the surface. So let's take a look at this surface. We have z is equal to this, which is the top part of the unit sphere. Because if you square both sides, right, you get z squared equals all this stuff. Move things over, you get x squared plus y squared plus z squared equals 1, which would be the whole sphere. But by solving for z and only looking at the positive root, you get just the top half. So that's this. And then what about this? What's this down here? This is a circle if that was equal 1, but it's less than or equal to 1. So it's every circle with radius 1 and smaller. So it's a disk, and z is 0 means you're on the ground. So it's the bottom of this, isn't it? So you have the hemisphere up here. That's one part of the surface, and then the bottom of it. You see, you have to close it off, right? If you don't have this, it's not closed. So if I give you a problem like this and I don't give you that part, you can't use divergence theorem. This part has to be here to use divergence theorem, so it encloses a solid. We good? E is in here. Div f. Div f. All right, well, div f. Here we go. All right, it is the partial with respect to x of this, right? Plus the partial with respect to y of this, plus partial with respect to z of this. Without loss of generality, if I do one of these, they should all look the same, right? They should all have elements that look pretty much the same. So let's just focus our attention on one of those. I just erased this. I'm going to need it in a little while, but all right, what is the partial with respect to x of x root x squared plus y squared plus z squared? And I heard product rule, right? Here's your product. So good old Cal 1, you're going to say that this is going to be derivative of this times this. So how about just the root of all that stuff, right? I'm going to call it root j. J stands for junk. That is the root of the junk. Yes? Okay. Plus product rule. Plus the derivative of root of that root stuff is 1 over 2 times the root of that junk, right? This is just 1 over 2 times the root of that junk. Times the derivative of what's inside with respect to x, which is 2x, times the original function, which was x. So that's what it would look like, right? Let's try and clean that up a little bit. The 2's would cancel. You would have the root of this junk plus x squared over the root of the junk. Yeah? Fine by me. What should this one look like? Same thing except y squared, right? This one should look like same thing, z squared. Let's see. Let's get a common denominator for this one right now. Can we do that? What would the common, if we got a common denominator, I'd have to put like a root junk on the bottom here, top and bottom. So when I hit this root junk with root junk, it's going to become just junk. So I'm going to have the junk plus x squared. I hope you're okay with this junk thing. Have I used junk in here before? Okay. I'm taking it from one of my professors. He loved to use the junk, so I think it's within fair game here. So that's what we get, j plus x squared over root junk. So now my div. I'm going to have junk plus x squared over root junk plus this one will be junk plus y squared over root junk. And this one will be junk plus z squared over root junk. With me? Right now, this doesn't look very nice that we have all this happening, but I think it'll be okay. We have common denominator here. We already do, so we can put them all together, which is junk plus junk plus junk, right? Which is just 3 junks. This is fun. Plus x squared plus y squared plus z squared over root junk. Okay, it's time for us to stop being lazy. What is junk? X squared plus y squared plus z squared, isn't it? So this is 3x squared plus y squared plus 3x squared plus 3y squared plus 3z squared plus x squared plus y squared plus z squared, which is really just 4 of the x squared plus y squared plus z squareds. Agreed? Over the square root of x squared plus y squared plus z squared. And these are the same things, right? Just different powers. So subtract exponents. This is just going to be 4 root square root x squared plus y squared plus z squared. Yes? This is to the first power, and that's this to the half power. So 1 minus a half is a half, and that's the same as the square root. Sure? Yeah? Okay. So that's the div. Let me double check. That does not look familiar. Yes, it is. That is good. Okay. We've got to integrate this. Okay. So I'm supposed to do the triple integral over e of 4 is going to come out square root of x squared plus y squared plus z squared dv. Remembering that my solid E came from the top part of the hemisphere, right? Is there a way that you can somehow give me the controls that I need on x, y, and z in order to create this thing here? Spherical coordinates. Awesome. Good. Go to spherical coordinates. Right? It's a sphere. Perfect for spherical coordinates. What are the conversions for spherical coordinates? X is equal to something, something. Y is equal to something, something. Z is equal to something, something. Yes? But what is x squared plus y squared plus z squared equal to? That's if it's a unit circle. This is a unit sphere, but when we do the conversions, remember when we do polar conversions, we say r cosine theta, r sine theta? We don't fix that r, do we? What do we use in spherical? Well, we use phi or phi, whatever. We use theta, and we use not r. It's the Greek r. Rho. So if you go back to spherical, we have conversions for x, y, and z, and then we have an identity that says x squared plus y squared plus z squared equals rho squared. So this right here is rho squared square root.
So it's just rho.
It's just rho. Y'all okay with this? We're going to spherical. Spherical. So we're going to go 4 integral, triple integral. This is going to be rho. But because we went to spherical, you must include something in this. The Jacobian determinant, which was rho, was it squared? Oh, are you saying it's going to be squared? Yeah, no, me too. Rho, we'll double check it, but it is sine phi. That is right. Let's just double check it. I think you might be right. Who has our spherical? I don't have chapter. This would be chapter 12, spherical coordinates. No one has it? Well, you know, I have the work written down here, so shoot, I should just look at it. What? Do you have rho sign? Now my work doesn't look right here. For some reason, I converted this over to rho squared. That's not right.
Rho squared sine phi.
Rho squared. Good job. Rho squared. So this is the Jacobian. Just like with polar conversion, you have to include the r. With spherical conversion, you have to include rho squared sine phi. And then I need my integration stuff. So I've now turned everything in terms of theta, phi, and rho, right? Those are my 3 variables. So if we're going to try and draw this sphere, what is my restriction on theta? 0 to 2 pi, because remember, theta is going to be this thing, right? So I want to be able to go all the way around. Phi?
0 to 2.
So from the top, only half the sphere. So to pi over 2, right? So from straight up, you only want to come down this far. So 0 to pi over 2. And then on rho, it's your radius. Remember, we're creating the solid here, so 0 to 1. And the order of integration, does it matter? Doesn't matter, they're all constants, right? So let me just go like 0, 1, 0 pi over 2, and 0, 2 pi. And that's going to have to be d theta, d phi, d pho, d phum, whatever you want, d rho.
Is that right?
Answer is 2 pi. I won't compute it. Okay? All right, this is it. This is the last. Oh my gosh, I only have talked too much. I don't know about this last one. Man. You know what? I don't think I'm going to do this last one. I tell you what, I will send you a link to the video where I do this problem if you're interested in it. It's not something I would test you on. It's verifying Coulomb's law from electromagnetic. No, Coulomb's law sound familiar at all to you? Okay, so it's just verifying that, showing it's true. It's a cool problem, but since I already have it on video and you can watch it if you want to type thing, I thought it would be interesting if we took like 10 minutes to talk about just like calculus in general. Like now that we're kind of at the end of it, like draw a picture of calculus. It's sad. It's just like that. I just really thought it would be interesting if we could go back and look at I wanted to try and see if we could figure out what is at the heart of calculus. Like what is the piece that everything depends on? The limit. It's all the limit, right? If you were to have to now summarize what calculus is really all about, it's about the limit. So let's just start with the limit here in the middle. The idea of the limit, when it's first introduced in Cal 1, you really have no idea where this is going to lead you. But the limit is the idea that you can let something approach something without actually ever getting there. Right? Limit as x approaches 0. Limit as x approaches infinity. Whatever it is, it's the idea of the difference between college algebra, where you get a function, you plug in the value 2. That means you actually let the value of x be 2. Versus calculus, where you want to see what the function's doing close to 2 without actually being at 2, right? And initially, you're like, why would I ever need that, right? Why would I ever need to let a function get close to, or to get close without actually being there? But what do we develop from this limit? What's one of the things that we get from this? The derivative, right? The derivative comes from the limit. The derivative is actually, by definition, the limit as h goes to 0 of f of x plus h minus f of x over h. That's the definition of the derivative of a function f, right? At the value x. So right away from the limit, we're able to develop this idea of a derivative. Okay, what else comes from the limit? Yeah, pretty much there's nothing you can say that's going to be wrong as long as you say something that involves calculus. Okay, so let's see. What about the integral? All right, well, the integral, what was the definition of the integral? Well, it was this thing, right? And that was like f dx. That was the first integral we saw in Cal 2. But I tried to show you that that was just a summation of rectangles, right? You're like taking the width, multiplying by the height, adding them up. Where's the limit in this one, though? Yes, but like how is the limit involved in this sum? It's an infinite amount of rectangles, right? So what you do is you take your function, you cut it up into n rectangles. So there's n rectangles here. And if you actually do n rectangles, you compute the answer, you're going to get a number, and that answer is going to be wrong. It's going to be an approximation. The way to get the exact answer is to let n, the number of rectangles, go to infinity. That's a limit, right? You take the limit as n goes to infinity of this sum. So there is a limit out here as something goes to infinity. It's complicated the way you plug it in, but it allows the number of rectangles to go to infinity. And it's really by making the width of these go smaller, right? So the integral, right? The derivative are born from the limit. You need the limit to do those. What else? Series. So where did we need? You don't remember? Okay, so where would we need limits in series? Okay, so within some of the tests for series, you need to take limits, right? The series itself, the definition of a series, an infinite series, is that we say that S converges if the limit as n goes to infinity of S sub n equals S. That meant what we did is we looked at the partial sums. We would take the series and we would add it up out to n and say, look at that answer. Now what happens as n goes to infinity? If that converges to a number, then that's the series, that's the sum of the series. Right? So we need the limit for series. There's more places, because in series like Maclaurin series, Taylor series, you need derivatives, but derivatives, you need limits. So, I mean, is there anything you can think of in Cal 1, Cal 2, and Cal 3 that did not need the limit? Other than like graph x squared. I know you don't need the limit for that, but I'm saying anything that was of value in calculus 1, 2, or 3 that did not depend on the limit somewhere. Some of you are in differential equations right now, right? So if you're in differential equations, diffie q, well, your differential equations, you're taking derivatives, right? Whether they be partial derivatives or just regular old derivatives, you need a limit. If you're going to do a derivative of anything, you need the limit. There is no such thing as the definition of a derivative without a limit. You need the limit for it. So the entire branch of mathematics called differential equations relies on the limit idea.
Even in matrices, you have limits.
What's that?
Even in matrices,
Yeah.
system of equations.
So imagine, I'm just talking about, because differential equations is sometimes mentioned in calculus textbooks, like they'll have like one section for it. Man, what did we do? I mean, was that all we did in calculus? We did vectors. Okay, so we did vectors, right? That didn't involve limits until we got to vector functions and then started talking about tangents and lengths, and then
But weren't vectors just ways to define points now?
vectors were just so we could do calculus. We introduced the idea of vectors just to give ourselves a structure to work with. That's all we needed the vectors for, is just to have something to work with. Without that, we couldn't draw curves, in three-dimensional space without vectors and vector functions. I mean, most of the time when you talk about calculus, you say that calculus is broken up into two different pieces. It's differential calculus and integral calculus. And you could say, that this somewhere fits in there in between, kind of. And then series is part of both also. So, yeah, I mean, I guess we could keep listing things out, like specific things like volumes of surfaces or volumes of functions that are revolved. Well, that was integration, so it goes back. So pretty much anything relied on the limit. So that was the big step forward. That was the big leap that Newton and Leibniz were able to do, is to remove themselves from the idea of finite arithmetic, where everything was in a very static state, and they allowed things to continually move, to repeat an operation like series, to continually repeat a process over and over and over. And that, of course, I mean, imagine without that idea, you don't have any of these branches. So the limit is a big deal. All right, well, it's been fun. What do y'all want to do now? Talk about the final? All right, so when is the final?
Monday.
Monday, so you get no time to rest.
0.
I thought I talked about it last time.
Yeah, you had like a number of amount of problems and like what you tested over before. What can we bring? Like all this?
Oh yeah, let's talk about that. Let's talk about what you can bring to the test.
Yeah, can I read the book? Wait, what can I do?
No. Well, you can have all those formulas, right? Shall we check Canvas just to make sure you know what's there? Well, let's see what's there first. Didn't save it. See if I can remember this. Okay, if you go to Files, and should have formulas here somewhere. Formulas you can bring to the final. There we go. So you've got your basic formulas that are the ones that are like out of the back of the book. You got these, and there's like 6 pages of those or something. And then you have the Chapter 13 summary, right, which is this enormous 16-page packet of things. Sorry, you'll have to go print that out. And that one that I was concerned about, that special case, this was that special case. And I only gave you one of the 3 special cases here, so that's why I'm going to attach the other one. Okay, so that's what's in here.
We can't write them. That's about it, right?
No calculus?
Oh, you can use a calculator. Just thinking here.
Is it gonna be like the midterm where it's like pretty much just a whole bunch of homework questions?
Well, I mean, that's my intention is to make it homework, like homework problems.
Or is it gonna like start at like 12.5 or like over everything?
Well, you're going to have, so think about this. If I ask you to do a problem with divergence, right? I could force you to do a triple integral in spherical coordinates, right? So it's very unlikely that I'm going to give you a triple integral in spherical coordinates by itself, right? There's no need to test you on cylindrical coordinates because I can give you a problem where you need to use cylindrical coordinates, right? So when we get to chapter 13, it's almost all incorporated in that chapter, isn't it? I mean, pretty much everything from the midterm on. I'm not going to go to anything before the midterm. So the only thing I'd say that's really missing in this is the Lagrange multipliers. That's the one that's not involved with this that we didn't do on the midterm. So on the Lagrange multipliers, I plan on giving you a function of 3 variables with 1 constraint. And I want to make it where it's very straightforward, like no complicated, crazy scenarios. Just show me you know what to do, which is what? Take the gradient of f and set it equal to lambda times the gradient of g, where f is your function and g is your constraint, right? One constraint, function of 3 variables. Yeah.
You'll have X, Y, and Z.
Oh, I accidentally unplugged that. Let's just see. All right, let's just see. Let's just take a look if this comes back up. Let's just see if I still have this up here. That's the wrong file. I'm still recording.
Oh, that's for pre-cal.
Yeah, no, that's for a pre-cal.
I don't know if that was- Yeah, name like pre-cal final, like-
No. Lagrange multipliers, triple integral. This one. Now look, I'm just showing you a final I gave a class. I'm not, you can't be like, hey, you see, we're going to do a triple integral. This is not your final, okay? This is a triple integral over a scalar function. This is a line integral, but it's not over a closed curve. So you have to actually, well, I give you the parametric function. So really, this is just purely computational. You just have to know what to do here. This one, I tell them use the fundamental theorem of line integrals. So look, out of the problems that I'm seeing here, 1, 2, 3. What are you thinking for this one? Just by looking at this, what are you thinking? Yes?
That's going to be the one with closed. I forgot.
What?
The theorem.
Green's theorem. You should be, just when you look at that, you should be thinking, look, I've got this weird, crazy curve. I'm doing a line integral, but it's enclosing a region. That's probably Green's theorem. The Green's theorem will give you polar coordinates, right? So we've got like 1, 2, 3, maybe 4. This is all chapter 13. Surface area of a cone. This is chapter 13. Flux over across the surfaces S1 and S2 shown below. So I probably labeled it for them on the printout, but it's not closed. It's not closed. It's only 2 surfaces. It would have to have the front, back, bottom, and top. So they actually had to compute the flux breakdown. This one, line integral over some crazy vector field. And the curve is the intersection of these two things. So Stokes' theorem probably for that, because that curve encloses a surface, and you know that surface. It's a special case where z is a function of x and y, and then you can use the shortcut.
You have old exams.
Do what?
Would you be able to post old exams for us?
I'm showing you one right now.
Yeah, let's go back in the video.
Yeah.
Okay.
And then I gave them a problem where I had a solid region here, and I'm talking about the surface around it, and I was asking them to calculate the flux, and it was the last problem on the test.
Can we,
And they probably
variables
did the what?
like that?
They probably did the divergence on that. Can what?
Can we keep the variables nice like that?
Variables nice like that?
Like in the midterm, you really challenge us to remember how to do certain things with.
I don't remember the midterm being anything too far away from
Nothing that we shouldn't.
the homework.
Felt like it was a calculus.
I think I can say this. I think that the final is going to basically determine whether or not you've been doing your homework. If you've been doing your homework, this should be okay. If you're not and you're planning on spending the next 4 days figuring out how to do all of Chapter 13's homework, then when you walk into the final, it's not going to look familiar to you and you're probably going to be in trouble. Because all of Chapter 13 is about recognizing what you need to do and having enough background and practice that you aren't sitting there spending 20 minutes going, what formula is this? You know, you're trying to do a line integral and it's a surface integral, you know? So, yeah. Yes?
Do people usually finish the final?
Pardon?
Do people usually finish the final or do they take up the whole time?
Historically, they take the whole time, yeah. But that's again, that becomes a function of I always try and design a test for a person who's pretty okay with what's going on is going to get through the test. But if, like I said, if you're sitting there for 20 minutes looking at a problem going, I don't know what to do, then you're going to probably run out of time.
Yeah.
So, make this a little bigger. When I talk about pattern recognition, what I mean is when you see this, you need to see that that's the triple integral of a scalar function, which has nothing to do with flux or anything else or no vector functions. It's just a scalar integral. You need to figure out what this region looks like, and you need to break down the restrictions on x, y, and z, or maybe you'll have to do a polar region. This is kind of like the end of the problem that we just did for div. It's kind of like at the very end of the div problem, we just had a triple integral over volume, right? This one, as soon as you see that, you should be thinking work. And you should be flipping through all the things that packet of formulas that have to do with f.dr. And then you look at that, you say, okay, here's work. Now let me think about what C is. Well, C is this curve, and that curve is not closed. So once it's not closed, you throw out Green's theorem. And then you say, all right, do I have the potential function? Little f. Because if you have the potential function, what can you do? Fundamental theorem of line integrals, right? But you don't have the potential function. It wasn't given to you here, right? So you could go try and get it, right? You might want to check if it's conservative because it may not be. So do not go look for the potential function if it's not conservative. How do you check if it's conservative? Well, it's a three-dimensional vector field. What's the check? Well, this is why you have until Monday to study. Okay? Something is zero, right? Curl. Curl is the zero vector. All right, so here, this one, use the fundamental theorem. Now, imagine I had not said that. Then you have this. It's almost like the same problem from above, meaning it's a line integral over a curve with a vector field. They look almost the same. I instruct them to use a fundamental theorem of line integrals because you can get the potential function from this. So this is a conservative vector field. So you get little f. What do you do once you get little f? Plug in the endpoints. The endpoints you get from plugging in 0 and 1 into the curve function. Now, if it's going to take you 30 minutes to sort that out during the test, that's what I'm saying, you're going to have trouble. Let's look at this next one. Work, right? Work, curve, field. Okay, so this is just like the previous two. Just like the previous two. However, my curve is extremely complicated, and I would actually have to break it into 1, 2, 3, 4 different curves and then do my work across each of the curves, right? But because of Green's theorem, I can actually look at this area instead and turn this into a double integral of, what goes in the double integral? Partial of q with respect to x minus partial of p with respect to y. What's the partial of q with respect to x? Partial of q with respect to x. 3x squared plus 3y squared. What's the partial of p with respect to y? Okay, so 3x squared plus 3y squared, right? X squared plus y squared is going to be r squared. It's going to go to polar, and that's perfect because this region is a polar region. This polar region can be defined r's between 1 and 2, and theta's between 0 and pi, and then you're in business. Just don't forget the other r from the polar. So again, if that takes you 15 minutes to figure out that that's Green's, I mean, or if you do this going around 1, 2, 3, 4, you've just eaten up about a quarter of the test time that you have. You don't want to do that. Surface area. Surface area of a cone. We did one of these in class. This is kind of going backwards. This actually goes, oh, no. Surface area came after line integral. I take that back. This is in order. So flux, cross surface, we already kind of talked about that a little bit, but when you break down S1 and S2 for this surface right here, right, when you do this surface right here, you use the normal vector probably. That would work pretty good. And I didn't give them, when I printed it out, I showed them what this function was. It's not on here. The reason why this one should be done using Stokes' theorem, what should tip you off on this is that the picture shows that you have this surface in between, right? Because it's the intersection of these two things. Right? This is a cylinder. Sorry. This is your cylinder going up the z-axis, and this is your surface. So you got your surface and your cylinder. So surface straight down is going to be a circle on the ground. Div. What's the div of this? 4x cubed, 0, plus... Wait a minute. 4x cubed, 0, so plus 4xy squared. 4x cubed plus 4xy squared. And then what you'll do is you'll define this region. So polar again on this, or cylindrical, however you want to say it. Limits of integration. What would that be? Hold on. What's the div of this? The div of this... You realize that I'm very unhappy that I'm showing this to you right now, right? That means I really have to think about each problem that I'm going to make for this test. Like I can't just go grab one of these and use one now. You've just ruined my day, okay? You've just ruined my day. Plus 4xy squared. And if I pull out an x and a 4, what am I left with? X squared plus y squared. Oh, this should probably go to polar, right? Because when I go to integrate this on the ground, like that cylinder on the ground, it's going to be polar. That'll be r squared. This will be 4. X will probably be replaced with r cosine theta. So it's going to be like 4r cosine theta times r squared times r. So you're going to, and then you just integrate and you're done. Yeah. A lot of 13 in here. A lot of 13 in here.
We basically, like, say we have like an arithmetic error, we just run it and show that we know the calculus.
Yeah, I want to see the work. Yeah, I mean,
We'll do the work, but I'm saying, like, if we do like an arithmetic error, just run with it. Obviously, we won't.
if you do arithmetic error, run with it.
Like our final answer is off, but we show that we understand the calculus.
Oh, yeah, okay, yeah, that's the way it's always been. If you have, some sort of negative sign that gets messed up or something and everything else is wrong based on that mistake, as long as I can identify where it happened, then you'll get partial credit for it, depending on the severity of the mistake. Because we all make mistakes. But it's just, sometimes when someone misses like a little minus sign, sometimes I don't even want to take off, but at the same time, it's like this other person didn't miss it, So how do I distinguish between the two? -1 or something like that, yeah. All right, well, I hope you all have enjoyed the calculus sequence, and it's over. Well, it'll be over on Monday.
Are the take-home exams graded the last?
I don't have those finished. Does anybody want their mini exam from the ones that you turned in that have not graded? Does anyone feel like they need that in order to study?
Just need the grade.
Just the grade? I'm going to work on them. I plan on getting them done this week.
Post answers online.
Post the answers online? I won't post the mini exam answers, sorry.
And then do you drop one of them?
Because I reuse those a lot, and I don't like the answers online. Huh? Yeah, I'm going to drop one. I have to see how many we have, but for sure one. Excuse me, Lynn. I'm sorry?